Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will have the opportunity to access it later on. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for either of our panelists, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your questions, and we'll try to get to as many as we can near the end of today's webinar. And also at the end of today's webinar, we are doing a drawing for 6 $25 Amazon gift cards. So please stick around. Hopefully you'll be one of our big lucky winners. All right, with that, let's go ahead and kick off today's webinar, which is Kubernetes, Reducing Infrastructure Cost and Complexity. Our speaker today is Kevin McGrath, who is the CTO at Spot. Kevin, thanks so much for joining me today. Welcome.
Thank you very much. Pleasure to be here. And yes, today we'll be going over Kubernetes and reducing infrastructure costs and complexity. We'll be going over a short slide deck. We're going to talk about Kubernetes, the makeup of Kubernetes, the architecture of Kubernetes, what you need to think about when you're deploying pods to Kubernetes and how your workloads work. We'll get into some specifics on how those workloads need to be put together, and then we'll go into a short demo. So,
all right, well, I'm going to take myself off camera now, put myself on mute, and let you get right to it.
All right, thank you very much. All right, everybody, thank you for joining. This is Kubernetes, reducing the cost of reducing infrastructure cost and complexity. So, in our first slide here, we have the anatomy of Kubernetes, and what we want to talk about here is how Kubernetes is set up and what we need to be concerned about with the major parts of Kubernetes. So there's a control plane. The control plane is where your scheduler, your API server, etcd. This is usually, about a 3 to 5 node implementation within the cluster, which is the brains of the operation of how things are actually orchestrated and where the decisions are made with Kubernetes. Then on the right, we have what's called the data plane. These are the worker nodes. This is the area of Kubernetes where you can have the nodes scale anywhere from 0 to thousands of workers. These workers will contain what's called kubelets, and then they'll also contain what's called services or ingress controllers on how data actually gets to the different pods that you deploy. So normally, and this isn't all cases, but in normal cases, you'll have a load balancer that sits out in front of your data plane management or your worker nodes. The traffic will come in through the load balancer and then get routed to the individual nodes within the Kubernetes cluster. And then based on the node agents that are running on the servers, your data will traverse the internal network to the pods that are deployed here. What we're going to focus mainly on today is that data plane management. The data plane management is where scale happens. This is where you will spend most of your dollars when it comes to running Kubernetes anywhere, on-premise or in the cloud. We're focusing on the cloud today. So when you deploy pods to nodes, there's a bunch of different scaling that happens. There's actually 2 different levels of scaling that happen within Kubernetes. First is obviously the scaling of the pods. So if you're familiar with Kubernetes today, work gets deployed to Kubernetes as pods. Pods contain containers. So the pods are a group of containers which have to get scheduled on the same node. So every time a pod gets scheduled, it has to have infrastructure as a service, or it has to have a VM where that pod can land. So Kubernetes itself, vanilla out of the box, is going to allow you to schedule these pods and to scale these pods. As these pods scale, the infrastructure also has to be able to support how these pods are scaling. So not only do you need to worry about how to scale your application and the pods that are supporting that application, but you also need to concern yourself with, do I have enough VM? Do I have enough infrastructure beneath these pods to meet the needs? And that's both for scaling up and scaling down. So as I said before, the first level of this scaling is horizontal pod scaling. So HPA is a feature within Kubernetes, which will check metrics by default every 30 seconds. And then based on parameters that you give the autoscaler, it will either increase or decrease the replica set that it's associated with to give you more or less pods. So if you base your HPA on CPU percentage, for instance, every time the average of CPU, let's say, hits 70%, then it's going to schedule more pods. Now, it's important to know scheduling more pods doesn't necessarily mean scheduling more infrastructure underneath. The HPA itself is concerned with how many pods are scaled to support the application. It is not directly tied to the infrastructure of where the pods need to land. The second form of scaling that's available in Kubernetes is vertical pod autoscaling. So in vertical pod autoscaling, as you can see here, the VPA checks metrics every 10 seconds. And what it's doing is it's checking to see if the pod is correctly sized for the amount of memory and CPU that it's actually using. When you schedule pods in Kubernetes, you give a request for how much memory and CPU that you want. You can also tell Kubernetes there's a limit that I never want a pod CPU and memory to go over. Now, with vertical pod autoscaling, what it's going to do is it's going to say, hey, I think you need more CPU, I think you need less CPU, and it's going to give recommendations on how to vertically scale that pod to make sure that you're not asking for more resources than you actually need. If you have a pod that's only using 1 gig of memory, but you have it configured to use 2, every single time that pod gets scheduled, down through the pod level to the infrastructure level, you're actually asking for 1 more gig of memory on a server at any given time, and you could actually be wasting a lot of resources and paying for resources that you don't use. So it's not only important to understand how to horizontally scale your infrastructure, but also vertically to make sure that you're not wasting resources along the way. So as you can tell, as we go through this, there's a slight problem here. Meeting application demands and also minimizing idle resources. So as Kubernetes infrastructure becomes larger and larger, you have to think about how am I deploying my pods? Are they efficient? Are they properly sized? Am I giving Kubernetes the right requests and limit information for my pod so I'm not going to end up wasting infrastructure, which I also need to ensure is correctly right-sized. So I am saving as much money as possible, or I'm running as efficiently as possible in the cloud. What we want to accomplish by the end of this is a scaling architecture that takes into account not only the pod size, but also how much you're spending on infrastructure, and if that infrastructure is actually matching the shape of the workloads that you're sending to the Kubernetes cluster. So to expand on this challenge a little more, it's something that we like to call the Tetris scaling challenge. What I'm going to show you is I'm going to show you a few slides of how things can kind of get out of whack between scheduling pods and then scheduling infrastructure underneath. Now, infrastructure that you bring to Kubernetes can be any type of infrastructure in the cloud. You can use one single type of instance. You can use many types of instances. Kubernetes cares about the number of CPUs and the amount of memory it has available to schedule pods. Beyond that, you can bring anything you want. So you can be as cost efficient as you want. You can bring what's called spot instances. You can bring on-demand instances, reserved instances. You have all of these options on how to bring infrastructure to your cluster. Now, when you bring that to your cluster, the scheduler of Kubernetes is going to say, I need to schedule a pod that has 3 vCPU and 4 gig of memory. This is an example. Now, when it looks at the infrastructure in total, you might actually have room for 3 CPU and 4 gig of memory. But if the infrastructure itself underlying that doesn't have 3 CPU and 4 gig of memory on a single VM, that pod is going to stay in pending state for a long time until it actually finds the infrastructure that it can put it on. So it's not in aggregate how much CPU and memory that you have in your cluster, but it's also, do you have enough CPU and memory on a single instance to actually schedule this pod? Because remember, a pod is a combination of containers that have to run on the same VM. So if Kubernetes can't find that in your infrastructure, it's not going to schedule this pod, and this pod is going to stay unscheduled. The second is sometimes you can bring the wrong node type, you can bring the wrong infrastructure to the Kubernetes cluster. So if we have a pod that's coming in that needs 3 vCPU and 4 gig of RAM, but the next instance that comes in that gets scaled into the Kubernetes cluster is an M3 medium, for example, from as an AWS example, then this pod is also not going to get scheduled because that infrastructure is not going to bring enough. In aggregate, it'll bring enough vCPU and memory to the cluster, but it won't bring enough for any one VM to actually run that pod. And then lastly, we not only need to think about scale up, but we need to think about scale down. And we need to think about what types of instances are brought to the Kubernetes cluster. And then if one of those instances go away, what would happen to the pods that are scheduled on that instance? Would those pods have a place to move? And if you don't have the right makeup of instances backing up the Kubernetes cluster, if one of them goes away, it's possible that the pods that were sitting on that VM won't be able to find other places in the cluster to run. So as you can see here, we dropped a rather large instance out of the mix, and now we have nowhere for these pods to run. We need to go find infrastructure again where these pods are not going to restart. So that brings us to what we like to call a different approach, or container-driven scaling. So what we want to do is not think about the infrastructure at the end of the day. What we want to do is deploy applications as pod to Kubernetes and then have everything magically work. We don't want to have to think about how to do this 2-level scaling, which is actually, has to go on all the time. So with a containers first philosophy, what we're looking at is instance size, type, and pricing is determined based on the pods that are being scheduled to the cluster, while honoring all the labels, the taints, tolerations, and network storage requirements that go into native Kubernetes deployments. Pending pods should be able to find instances that meet their vCPU and memory requirements. Taints and tolerations should take into account on whether something should be running with a GPU-based instance or whether it should be an on-demand-based instance as compared to a excess capacity or reserved instance, if those are makeups of your applications and how you want them to run. What needs to happen in this situation is that pods dictate how the infrastructure should be set up, and then the infrastructure should automatically meet those demands without you having to keep 2 sets of rules for scaling policies. So real quick again, we're just going to go over the control plane, the data plane. The control plane is any scheduler that you can think of. So the control plane, whether it's EKS, GKE, any Kubernetes, OpenShift, Docker Swarm, ECS, that can be absolutely anything you want it to be. Again, it's a small part of the cluster, probably 3 to 5 nodes. The data plane is what we're talking about here with all the different types of instances, all the worker nodes, all the pods. So to achieve this serverless or quote unquote nodeless experience, what are we actually talking about? What's the definition of this? This means no management of underlying infrastructure. You don't want to have to decide what infrastructure comes in and out of the cluster and when. You want to be able to scale by request, and you want to be able to scale based on the pod's needs and not some other metric. You want to base it on your workloads. You want utility billing. You want to pay for what you use, and you want to eliminate waste wherever possible. You want to be able to scale to 0. You want to be able to take all your pods and scale them to 0 and then have that infrastructure go away. And then you want to be able to have fast scaling. You don't want to have to wait too long for thresholds. You want to be able to schedule pods and then have those pods actually land on VMs that can run them at a very reasonable amount of time. So real quick, we're going to go through some cost numbers real quick on what shape and size of a pod request and how it lands on infrastructure and what that can mean for you cost-wise. So in this first example, we have a pod that requires about 6,500 megs of memory, 1.5 CPUs. And we're going to show you that within the same family, we're going to use AWS examples for this. So within the M5 family, we're going to schedule this pod multiple times across different sizes. And you can see for this particular example, as we scale up to a M5 2X large, we can actually run a lot more of these pods for considerably less. We can reduce our costs by 20% just by running more of these pods on a larger instance. Now, this isn't necessarily always the case. You always have to take into account that your memory to CPU ratio can be very specific for the app that you're running, and that will dictate what the most reliable infrastructure for efficiency that you can run. But in this particular example, you can see that as we get a bigger instance, we can run more of these pods for less money. So scaling M5 2X large is a lot more efficient money-wise than it is to scale an M5 large 4 times as many times. So it's not just as simple as taking any instance in a family and then scaling that at an exact multiple, because sometimes your pods won't necessarily match that same multiple that the instances have. So let's take another example of outside the family, taking a look at instances from different families. So we're going to take a very similar pod, this time with 6,500 megs of memory and 1.8 vCPUs this time. But we're going to show you that if we were to scale with a C5 extra large or an M5 extra large, there's a 43% difference for being able to fit the same max number of pods on both of those instances. So we're able, or not the same exact, but we, excuse me, we can have the instance vCPU as 4 on both. And then we can see that scaling on both of those servers will result in a much bigger price difference between the two. All right. So what are EC2 spot instances? And we're going to bring a new term into the mix now. We've been talking a lot about just Kubernetes, like default Kubernetes, what you need to think about, what you need to scale, why you need to think about pod sizes, why you need to think about VM sizes, why you need to think about scaling both of those. And we know that our optimal infrastructure is to deploy pods and not worry about the infrastructure at all. So how do we make that infrastructure as efficient and cost-effective as possible? So EC2 spot instances, or just spot instances in general, are excess capacity. Spot instances actually exist on all the major clouds: Azure, AWS, Alibaba, GCP. Providers offer these instances at an 80% discount over the cost of on-demand. However, they give you no SLA. They can take these instances back from you at any time. Different cloud providers offer different time limits on these instances, but a general rule of thumb is that the price is going to fluctuate on these instances, maybe every hour. And then the providers at any given time can decide to take these instances back if they find their on-demand capacity is filling up and they need to take from the excess capacity market and give it to the on-demand market. I'm going to talk more about that in a minute if it sounds confusing. So across the different clouds, we have AWS, Azure, and Google Cloud. They're called different things in the different clouds, but what you should know is that there's a variable price in AWS, there's fixed prices in Azure and Google. There's a small shutdown lead time that the providers might give you, anywhere from 30 seconds to 2 minutes. And only in Google is there a maximum time also. So in Google, a preemptible VM cannot last longer than 24 hours. So you're going to be replacing your VM every 24 hours. What we're showing here is that you have these options. Going to any cloud provider, you have an option to run your compute for 80% less than what you run it for today on demand. Now, this adds another complexity to management in the whole thing, where now you're not only managing, the scaling of pods, the scaling of infrastructure, but which spot, what's my ratio between on-demand and spot? How much money do I want to push for savings? And then how do I manage instances coming in and out of my cluster maybe more often than I'm used to? So how should I plan for interruptions? Spot instances will be preempted. That's the name of the game, that they will get pulled back. You need to be prepared for this. Each cloud provider has their different notification mechanisms, as we talked about. Your capacity of your cluster will be affected when these come through. So it's very, very important that you stay in front of this type of activity where the cloud provider comes in and takes it from you. You want to make sure you're listening to these notifications, or even better, have a system set up so you can kind of predict it yourself. Then you want to know what happens to your state of your application if an instance is lost or a pod needs to be rescheduled. Fortunately, with Kubernetes workloads in general by default are already designed and architected to handle the pod moving from one VM to another VM. So in a lot of cases, when you're running Kubernetes applications, you've already kind of solved for the, hey, if something fails, what happens? And so that's great with Kubernetes applications, that in most cases you solved for this one already. And then these situations can all be handled. You can actually make this a very, very graceful mechanism within your Kubernetes cluster, and we'll talk about that later on. So just a little bit more info about how the terms that we use to define spot markets and how they exist. There's two types of pools. There's a capacity pool inside the providers, and then there's a spot pool. And just so you know how these two usually line up with one another, is a capacity pool is a set of instances that share the same region, availability zone, OS, hardware. And then the spot pool has its own availability and price that's kind of determined by the supply and demand of that capacity pool. What's important to note here is that since on-demand and spot instances share a capacity pool, spot prices can fluctuate not only due to the amount of spot that's being used, but also to the amount of on-demand. And also it's within like a specific data center and availability zone where that exists. So some other customer comes in to a cloud provider and starts using a ton of a certain instance type and a certain AZ, that could start affecting the price whether they're using spot or not. Just as long as that capacity pool gets congested, that will affect the spot pool, and in turn affect how often instances are being reclaimed. So this is a visualization of what in AWS terms, what a data center might look like in US West 1A, US West 1B, and then an example of different instance types and what their availability is within those actual data centers that AWS runs. And then as another visualization of this, if you look at the blue or the teal, if that's the right color for that, if those were interruptions that were happening in a market, what we're just trying to show you here is that there can be any number of capacity pool in a zone, but within that zone, very different things can be happening based on what interruptions are happening at any given time. So this could all be one region, this could all be US East 1, but in 1A, 1B, and 1C, you have very different things happening with the markets. So real quick on a pricing strategy, when you're dealing with spot instances or you're dealing with excess capacity on any of the cloud providers, it's important to know that when you're making the move from on-demand to spot, there's a lot of different ways to save money. And this brings in yet another component to think about, is that if you have a pod or if you have an application, and this goes for anything Kubernetes or even beyond Kubernetes, if you have an on-demand instance that normally runs with 4 vCPU and 16 gigs of memory, that might cost you 20 cents an hour. Now, what we just want to show here is that all of the instances below will actually cost less money than that on-demand price. So you can run instances that are larger, instances of different families. You have a lot of leeway on how you can run instances for less money than you were running with on-demand today. So if you take this knowledge and then you combine it with the shape and size of your pods and then how they fit on an instance, and you combine that with how you want to scale your cluster, and you put that all magically together, these are all the pieces of the puzzle that you want to put together to run your Kubernetes cluster as efficiently as possible. All right, so I've been talking about a lot about generic use of Kubernetes, generic use of the cloud providers, generic use of how to deal with pricing, how to deal with excess capacity. I am going to go through a few slides here quickly on Spot and our product Ocean, and just explain how it ties all of this together and what we do to make all those things you need to think about kind of an easy button. So first of all, we take serverless containers, nodeless containers, whatever you want to call them. We take that to heart with Ocean. So all the things that I talked about coming up to this part of the presentation, container-driven auto-scaling, auto-detecting the pod, the task infrastructure requirements, figuring out what the shape and size of the pods are, what the best instances to get, but then also correlating those instances to what price we can get those instances for from the cloud provider, and putting all that together where we're watching the Kubernetes scheduler for you. That is what we're doing with Ocean. So what you do is you deploy pods as you've always deployed pods to Kubernetes. We have a small controller that sits on the Kubernetes cluster that's watching these pod requirements, and then our Ocean is providing that infrastructure for you, making all of these decisions for you so you don't have to do any of the work yourself. So what Ocean does is it ensures that all pods have resources to run, and we select the most suitable instance type. It's also very, very focused on maximizing that resource utilization, that Tetris game that we talked about at the beginning of the conversation. This is something that Ocean handles all on its own. Again, there's no configuration that you have to set for this to happen. It's constantly looking at all the different workloads, types, pod shapes, sizes, taints, tolerations. It's taking all that into account and making sure that you're scaling in the most efficient way possible on the infrastructure side. Again, you can bring your own control plane. This is, works with any Kubernetes that's running in the cloud. Doesn't matter if it's EKS, GKE, your own Kubernetes. It could be a COPS installation or K3S. Your most favorite management tool for Kubernetes works with everything because it works with native Kubernetes at the end of the day. And then between finding the right instances, finding the right cost, and maximizing the bin packing and the right sizing of the pods, you can save up to 90% on your infrastructure costs. By doing all the things that we talked about beforehand, putting all that together can save you so much money compared to what you might be doing just straight out of the box with Kubernetes and on-demand instances today. Furthermore, Ocean will also give you complete cost management and showback for everything that you're running. So all of the pods that get deployed, Ocean will show you the cost of that pod landing on either an on-demand or an excess capacity or a reserved instance. It'll show you what the cost of that pod is, or that namespace, or the entire cluster. It'll show you what you could have been running, what you are running, how efficient you're being. It'll also give you showback and chargeback information. So if you're running a very large organization, you could, split your departments by namespaces and then do chargeback based on the namespaces and how much that namespace is actually costing you to run. Or you could do namespaces by application. However you manage Kubernetes today, Ocean can kind of break down and slice and dice that information for you and the chargeback information for you. We'll also give you vertical container auto-scaling. We'll measure in real time the vCPU and memory pods. We'll give you recommendations, and we also give you automated ways to deal with vertical pod auto-scaling. All right. So without further ado, we're going to jump to a demo. I will let everybody know that this demo is pre-recorded. I'm going to talk over it. Just want to make sure that the demo goes as smoothly as possible. And we also wanted to show you a demo that does everything soup to nuts. Everything from creating a cluster to scaling your pods, getting the right infrastructure, and then actually scaling back down to zero. We wanted to show you all of that. Some of these operations take a while. We didn't want you to have to sit through all that. So I've done this demo on my own. Now I'm going to talk through it. Hopefully I talk through it well enough that we all get through it together. But I hope it's interesting for you. So I'm going to flip over to the demo. And then in here, I'm going to click the play button and we'll get started. What's going to happen, or before I click play, what we're going to do is we're going to create a cluster from scratch with EKS. We're going to show you how to set up an auto-scaling application. We're going to drive a bunch of fake traffic, or just test traffic, I should say, to that application. We're going to have the horizontal pod autoscaler that comes native with Kubernetes scale up. We're going to show you how Ocean can bring all that infrastructure to the system or to your cluster. scale up, meet the demands of the application, and then scale back down to 0. So I'll click play here, and hopefully this is working. And you can see that we're running our EKS-CTL create cluster command. Ocean is natively supported by EKS-CTL. We've contributed back up to the source here. Once the cluster is created, we can go ahead and start looking to make sure our cluster is good to go. So we're going to get our services. We're going to see that Kubernetes is running. Now we're going to take a look at our deployments, and we're going to make sure that the Ocean controller is running on the system. You can see it's not ready yet, but now it is. So now that the Ocean controller is running, we can go over to our console, and we can see that an EKS cluster was created. This cluster, the worker nodes, are going to be managed by Ocean. In the Ocean view, we can see we have 1 of 1 registered nodes, which is a default that happens with EKS. You can see on the screen that we give you a bunch of information. We give you the Kubernetes version. We give you how it was created. We can also click over to the nodes, and we can see our 1 live node that is running and the 5 management nodes that are needed by Kubernetes to go. So core DNS and some other default nodes are running on our cluster. So now we'll go back to the command line, and we'll clear things up. And what we're going to do now is we're going to start setting everything up. So we're going to set up the HPA, and we're also going to deploy what's called an echo server. So it's just going to echo back a response. That's what the application is. A very simple application, just going to echo back anything that we send to it. So you can see our echo server is up and running, 1 out of 1 pods available, and our HPA is all set up with a minimum of 1 pod and maximum of 100 pods. No traffic is moving here yet. You know, we don't have any target percentage at this point in time, but we do have a load balancer we can hit. So what we're going to do is we're going to copy this load balancer, and we're going to use it later. And what we're going to do is we're going to fire a bunch of requests at this load balancer to show you how to change the target percentage of the HPA and eventually get more infrastructure. So if we look at our pods, what we're going to show you is that the echo server is running, waiting for requests. And then we hit back to the overview. We're going to see that we're still 1 of 1 pods, everything's stable. So what we're going to do now is we're going to curl against that just to show you what the echo server does. It basically just pings back our HTTP requests. So everything's live, everything's up and running. We have 0% CPU. We have a very, very low threshold of 10% for this right now, so we can scale fast. This way, the HPA will engage a lot quicker than it would probably normally if you set it at 80 or 90%. What we're going to do here is we're going to set up an Elastic group. This is just another product of Spot. This is a way to manage auto-scaling applications. What we're going to do is we're going to fire up just a fleet of VMs whose only job it is to fire requests at our application running on Kubernetes right now. So what I'm doing is I'm modifying the user data of this Elastic group, and this Elastic group is going to manage a bunch of VMs whose only job is, if you know the open source project Vegeta, it's going to use Vegeta, and it's just going to fire a ton of requests at our cluster, and it's going to cause our HPA to react to scale up and need more infrastructure. So what we're going to do here is we're going to take the capacity from 0, and we're going to do 4 attack nodes, if you'd like to call them that. This will fire up in AWS. It's actually going to result in 4 Spot instances that are going to start the load on our Kubernetes cluster. So you can see that we now have 4 quote unquote load testing or attack nodes that we can use to start generating traffic to our test application. Now you can see here we've done a good job. So right off the bat, we're at 250% of our 10% of CPU that needs to be used. So we'll flip back to our Ocean cluster and check out the nodes. Now we still only have 1 node. We have 7 pods. So that's interesting. We saw it spike to 250%, and we had a 10% threshold. So let's see what's going on here. Let's go check out our HPA. And if we look at our HPA, you can see HPA only asked for 4 replicas so far. So since it only asked for 4 replicas, it launched 4 more pods, but it had places to put them. So we didn't have to scale up again. But in the background, what is happening is we noticed that HPA then went to 25 pods. So now that the HPA is asking for 25 pods, we're going to go back into our cluster and see that now we're scaling infrastructure, right? This is happening automatically for us. 22 pods were scheduled on the original instance that we have, 22 total, and now we're going to start scheduling pods on the second VM that we're bringing in. So now we have 22 plus 11. Let's see what our HBA says. It says we're at 16%, 15% of CPU, and it's still only asking for about 25 replicas right now. So what we're going to do is we're going to send more traffic because this isn't exciting enough yet. So we're going to increase our 4 to 8, and we're going to just create some more attack nodes, and we're going to send a lot more traffic to this application that we have running on Kubernetes. So now that we've changed our 4 instances over to 8 instances, we'll wait for those instances to become healthy. Once those instances become healthy, we're going to see a lot more traffic coming into our application again. So you can see now the HBA says we have a lot more traffic. Let's scale to 70 replicas. So if we go back to Ocean and we go back to look at the pods, we can see all the Echo servers that are all the Echo pods that are being scheduled. And if we come back, we'll see now that we're getting even more instance types. And I want you to notice that all of these instances are different sizes, and they're either based on vCPU and memory or the sheer price that instance is costing us. So we'll lean towards cheaper instances, even if it's not the exact makeup of vCPU and memory, as long as it's getting you the most efficient cost. And then you can see everything that's happening on the main overview of how many instances we're scaling up and of which types. And now our application is leveled off again. We're at 8% of our 10% target. We've scheduled all the pods that we need to schedule, and everything is running as it should. So what we're going to do now is we're going to scale back down to 0. We're going to take our target. We're going to drop our target of attackers from 8 to 0, or our load testers from 8 to 0. Once this happens, we're basically just shutting off the pipe. There's going to be no more requests coming into our application. As you can see here, our instances of load test nodes are now at 0. We'll go back to the Ocean cluster and we'll check on the HPA and see how the HPA is reacting to us turning off the spigot, if you will. So we'll get the HPA from kubectl. Hopefully still going, sorry. So we're at 8% of the 10%. Replicas is still 100. So we're gonna have to wait until the HPA actually drops the replicas from 100 down to 0. And once the HPA actually recognizes, that the traffic is gone and all the servers are actually dead, we'll see that there we go. Replicas 1, it's recommending 1 replica, so it's going to leave us with just 1 left. And then if we go to our Ocean cluster and we go to the nodes, we'll also see here that all the instances that are unnecessary are going to eventually drop off. So you can see that CPU's gone away, and eventually every single instance that we have, Ocean's going to recognize that we don't need them anymore and drop down to just the 1 instance. We need to be running the 1 replica of the pod that we have. And that does it for the demo. I know it was a lot. We tried to get, a full soup to nuts demo of everything from creating a cluster from scratch all the way through putting an application on, load testing that application, and then bringing that application down to 0. The only thing left here to do a total cleanup was to go back to EKS-CTL and saying, hey, remove my Kubernetes cluster, and we'd be all cleaned up here. So I hope everyone enjoyed the talk and the demo, all the different things you need to consider in the cloud. Hopefully you recognize Ocean as an easy button to put all this together for you too at the end of the day. And if you have any questions, you can always reach out to me, CattleGrep on Twitter, Kevin@spot.io email. And again, I'm Kevin McGrath, CTO at Spot. And I'll turn it over to Charlene and any questions that might have come up.
Awesome, awesome. Yeah, so plenty of time for questions, guys. If you have one, go ahead and use your GoToWebinar control panel and submit it, and we'll go ahead and dive right into the questions we have so far. Here's the first one for you, Kevin. How does Ocean collect EKS metrics for sizing recommendations, and which metrics does it collect?
All right, so that's a great question, and it actually EKS isn't even the most important part of the question here. EKS acts like any other Kubernetes cluster, so this answer goes for EKS or any Kubernetes that you're running. The controller is watching the metrics that come out of Kubernetes itself, right? And then we're sending those metrics back, the CPU, the memory requirements, any taints and tolerations that are associated with that pod. We're aggregating those. It gets sent up to our SaaS platform, and everything is decided on at the SaaS level, gets set back down to the Kubernetes cluster, and then we're deciding on how many VMs are needed or not needed for that pod to scale successfully.
All right, great. Our next question here, let's see. Do you see a lot of companies making the shift from ECS to EKS? If so, why and when?
Another good question, and I think both ECS and EKS are growing at their own rates. We do see a lot more customers adopting Kubernetes itself, but we also see customers scaling larger and larger with ECS. I think it's a design pattern that your DevOps team is going to take to heart. If you're someone who wants kind of the vanilla Kubernetes open source way to go, your DevOps team is going to take that, and EKS is going to be a great choice. If you're a DevOps team or you're a development team that is embedded in the AWS ecosystem and you're fine with using all of the AWS tools and they all just fit together well for you, I think you're going to pick ECS and you're going to scale with that. And we find that customers scale well with both. Yeah.
Excellent. All right, great. Plenty of time, guys. If you have a question, go ahead and use your GoToWebinar control panel. Next question here. Is there a tool out there that watches for spot instance eviction notices and transitions to reserved instances preemptively?
Right. So, well, Ocean does that, but there's also some open source tools. So I will say it is a big ecosystem. There are tools out there that will watch for the notifications. Most of all of those tools are reactive. And what Spot does differently is Spot is a predictive and proactive tool. So there's auto spotting, which is an open source project. There's also some scripts that you can get that are floating around there from AWS and other tools that you can load on your instances, and it'll watch for that 2-minute warning. And when the 2-minute warning comes up, you can build your own code around that to do the necessary things. What Spot and Ocean is going to do, it's taking all the information that we have in aggregate about all of the spot markets, all of our customers, puts it together, and we put together a predictive model to try to successfully launch these instances before they go away. So Ocean is always staying in front of where you need to be. So Ocean is going to realize a market is getting congested before you necessarily get an alert from the cloud provider itself, and we're going to start bringing instances in before they go away. Our goal is if you have 100 instances and you're going to lose 10, we're going to bring you up to 110 before you ever drop down to 90, right? So we'll bring you to 110, you'll be back down to 100, you'll be at full capacity. So there are ways you can do it yourself. Our platform goes a step further by aggregating all the statistics we get from all of our customers and keeping you up with an SLA.
Excellent, excellent. Okay, great. Let's see, here's a great question for you. Have you experienced some differences between AWS, GCP, and Azure Kubernetes implementations? And do you prefer any of them for some justified reason, or is it just a sort of familiarity? I can't say that concern. That's such a difficult word for me.
No, another great question, and this is kind of, I mean, I think this is a question we could talk about for a very long time.
Right, yeah.
I will say that if you want to be on the latest version of Kubernetes at any given time, Google is always releasing those. As Kubernetes is coming out with the versions, Google is releasing those very quickly. Amazon is a little bit further behind. Azure is actually pretty close to the release dates. I think what's more important is how I kind of answered one of the first questions is what's most comfortable for your team to develop in today? Are you an AWS shop? Are you a Google shop? Are you an Azure shop? That's probably going to be the bigger decision making of what we find in which one that you use. We don't see too many people switching just because of the management cluster. It's usually because of all the other tools that they're also using from the cloud provider around those management tools. So I think that it's going to be the bigger decision making, and I think it's personal to what you and your DevOps team do.
Awesome. All right. Great. Still plenty of time, guys. If you have a question, we've gotten some really great questions in, but like I said, there's plenty of time. If you want to go ahead and get a question in, go for it. Okay, here's the next question. How do you do auto scaling in Kubernetes at Spot?
How do we do it? Well, we use Ocean. So,
all right.
And you know, how do we do it? And to talk about what Ocean does again, real quick. We have a control. There's a small controller that sits on the Kubernetes cluster, and what it's doing is it's watching what the scheduler needs at any given time, sending that information back to our SaaS platform. Then the SaaS platform is looking at the historical trends of what the Kubernetes cluster has done in the past, and it's also predicting out what that Kubernetes cluster is going to need in the future. So Ocean has a lot of different features to it, whether it's headroom, where we're always making sure infrastructure is available for pods, or whether it's just getting in front of where your cluster normally scales and what your different launch configuration and pods scale to. So we lean heavily on our own product. We dog food at Spot. So we use Ocean at Spot. We use Elastic Group at Spot. And then for our customers, it's the same thing. So we're monitoring and watching everything that happens with their deployments, and then we're always staying in front of what those deployments need. What Ocean's goal is for there to never be an unscheduled pod. If there's an unscheduled pod, it has to be a configuration issue. It shouldn't be due to infrastructure. It shouldn't be due to anything else. We don't want any unscheduled pods to ever exist in a Kubernetes cluster. It's a metric we watch very closely.
Excellent. All right. All right, next question. Does Ocean work well across two AWS data centers, GCP, IP backhaul, or flat addresses? So does it work better with GCP?
So I think what the question is asking is like with federated federated distributions of Kubernetes, Ocean will manage your clusters in each cloud. How you federate the data back and forth for those, there's still up to you how you want to trunk that data between, whether you set up a VPN or IPsec tunnel or whatever you're trunking between. Ocean is not going to manage that link of the data movement for you, but Ocean will absolutely manage the clusters in the different clouds and kind of give you a common interface to manage both of those clusters.
All right, great. Next question, does Ocean provide medium or long-term trending?
Yes, so we provide trending on all the pods that you're deploying. When you go into the console, you can see full history on where the pods have been, what their memory is, what their CPU usage is. You can see all the logs of what Ocean is actually doing to your cluster over that time. So yeah, we provide a wide array of metrics that you can pull and store for your Kubernetes cluster.
All right. Well, I have I guess maybe a follow-up question to that, very related. How do the recommendations work? How many days of data, memory, and CPU do you need to analyze for the recommendation?
Right. So right now we're at like 3 days. We require like 3 days of metrics to come in before we're telling you for vertical right sizing, I should say. For vertical pod scaling, it's 3 days worth of metrics that we're looking at because you can't necessarily decide after an hour or 2 hours. Again, those are recommendations. We're not going to automatically start changing your pods on you just after 3 days worth of data, but you'll be able to start seeing what those recommendations are. Horizontal pod scaling is obviously very different. In infrastructure scaling, we start doing that instantly as soon as you install Ocean. We start horizontally scaling and getting infrastructure for you right away.
Excellent. Excellent. Okay, so we are about 11 minutes to the top of the hour. I think we have time for a couple more questions here. So if you have a question, it's not too late. Go ahead and submit it, and hopefully we'll be able to get to it. Here we go. Here's another one. What happens if there's a problem communicating with the SaaS? How robust is Ocean in that case?
Yeah, so we're going to start sending out a bunch of alerts. We're going to get alerts on our side as soon as communication has gone down. What's good to know is that nothing in the cluster is going to go away. The cluster is going to keep on running. The controller is still going to be collecting data. We do need to hook up that controller again to get like the intelligent scaling to click back on, but alarm bells start going off very quickly if we realize the controller's kind of lost communication, and we proactively jump on that from our side to contact and make sure everything gets hooked up again.
Excellent. Okay. Okay, here's a question for you. Have you tried the kind of serverless implementations for Kubernetes pods and services like AWS's Fargate or Azure AKS virtual nodes? How do you like them in terms of flexibility and cost reduction?
So I think they all have their benefits and drawbacks. So it depends on how, with Fargate, you're handing off a lot. If you have very simple applications where you don't need to kind of like fine tune the infrastructure underneath, or you don't need those things, you're allowed to run those applications outside of a private VPC and kind of lock down to where you are, or you're fine with not. Ocean allows you to kind of control more of the scaling. So you can control like the instance families that you use, the generations of families that you use. Like, even though we give you an easy button, we also give you a way to really, really fine tune the way that Ocean scales for you. So in a larger demo, we might show you all the different configurations options that exist in Ocean, all the networking options, storage options, infrastructure options that you can set and then kind of set and forget. With Fargate, you're just at the whim of whatever hardware they happen to be using for Fargate, which is fine for some applications. It's bad for others. It's also, there's storage implications, network implications, different latency back and forth between other applications you might be running within your account. So I think things like Fargate, things like ACI from Azure, I think they have their place, but I think our largest customers, people running thousands and thousands of nodes of Kubernetes, are still running, they're running Kubernetes, and we're helping them fine tune those clusters to run within their account.
Excellent, excellent. Okay, next question. What predictable model does Ocean use, and how is it different from out-of-the-box recommendations from AWS EKS?
Right, so out of the box, you're going to be using the metrics that exist from the metrics server, and what we do is we keep metrics over a much longer period of time, plus we can aggregate unidentifiable statistics from all of our customers together to understand how certain applications scale. So whether it's an Nginx server, Redis, or different things like that, like we can actually see the heuristics of, in aggregate, how applications are scaling, and not only that, how your applications are scaling over a longer period of time. And then we're running that through our own modeling service, where we use how we predict scaling with our spot predictions, with the knowledge of the markets and with the knowledge of applications, and we kind of throw that all together. And that's what the Spot SaaS platform is doing, which is different than the metric server. It's going basically on metrics. It's mostly point-in-time metrics. I believe by default, it might only be a few days or a week from the open source version of the cloud autoscaler that's in use today. And it's going to be more point in time of what's happening right now, whereas we're taking into account holidays, scale, when infrastructure, when as I said before, capacity pools are getting congested. We know the heuristics and the timelines of these things, so that all goes into our analysis.
All right, great. I think we have time for maybe 2 more questions. Let's see, what are the terms of your SLAs, and are they available for inspection?
Yeah, so the contract's available on the website if you want to read through all the terms. I believe it's still a link from the main website, and if not, send me an email and we'll send them to you.
Excellent, all right. Okay, let's see, I think we have time for 1 more here. Okay, here's one. After setting up my EKS cluster in Ocean, how long does it take before recommendations are ready?
Okay, yeah, I think this is very similar to one that we had before. For horizontal, again, horizontal scaling is going to work right out of the box. It's going to be about 3 days for vertical scaling recommendations to kick in.
All right, all right, all right. Let's do 1 more question, then we'll close it out. So,
all right.
how can I further reduce my spend in non-production environments?
Run a lot of excess capacity, especially for non-production environments. I would run, in fact, we have customers today, and this answers for production and non-production, to be honest with you. So we have customers today who, run 100% on excess capacity, whether it's AWS, Azure, or GCP. You can run everything from production grade applications to dev and test environments all on excess capacity. We recommend everybody to use, obviously, spot instances or preemptible VMs whenever possible. And yeah, I think that's the best way to run any application, whether it's production or development.
All right. Good stuff. Well, we're about 5 minutes to the top of the hour. So unfortunately, that is all the time that we have for question and answer period. If we didn't get to your question, I apologize, but please know that the folks at Spot are getting a copy of all of the questions that came in. So I'm sure they'll be more than happy to follow up with you offline and get your question answered. Also wanted to remind the audience that today's event has been recorded. So if you missed any or all of the event, or if you just want to watch it again, you will have the opportunity to do so. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. The webinar is also going to be living on the devops.com website, so you can always go look for it there. Just go to devops.com/webinars, look in the on demand section, and it should be right there waiting for you. Okay, before we close things out, I did mention at the top of the hour that we would be doing a drawing for 6 $25 Amazon gift cards. So let's go ahead and do that real quick. Our winners today are John M. Congratulations, John. Next winner today is Letitia R. Congratulations, Letitia. Third winner today, Ray A. Congratulations, Ray. Our fourth winner, Randy B. 1, 2, 3, 4. Yep. Okay. Fifth winner today, Alan S. Congratulations, Alan. And our final winner today is Jeff B. Congratulations, Jeff. We'll be following up with you guys by email with your $25 gift card. So please check your inbox. If it's not there, check your spam folder, because you know how they get stuck in the spam folder all the time. So Kevin, thank you very much for such a great presentation. Lots of great information. Love the demo. It was awesome. So thanks very much for that. And judging from the number of questions we got, I know the audience got a lot out of it too. So yeah, thanks again. Really do appreciate your expertise and your time.
Thank you for setting this up. It was a pleasure. Let's do it again.
All right. Sounds like a date. I also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I am signing off. Have a great day, everybody. Please stay safe.